So good morning, everyone. Welcome to the session, Minutes to Milliseconds. My name is Tafsir. I work as a Chief Software Architect for Careem. Careem is a ride-hailing company based out of Middle East, born and bred in Middle East, founded in 2012, and we have recently hit the Unicamel status a month back. Now, the reason we exist is to simplify and improve the lives of people and build an awesome organization that inspires. And we do that by using our ride-hailing platform and offering people safe and clean and transportation in the region. Now, before we dig into a solution, let's understand the region that we operate in. The region that we operate in is a bit different from the mature West that you see out here. And a lot of decisions that we took and a lot of technical decisions that we had to take were due to these ground conditions. So the first and foremost, infrastructure. The public infrastructure is not existent over there, and whatever there is scrappy and old. People are stuck in traffic for hours. Some of the regions are security challenged, and in some of the cities, estimating an ETA is a real challenge, because the intersections are quite far apart due to high driving speeds. If you miss an exit, the ETA becomes or goes exponentially high. The last and most important factor, social norms. In some of the regions that we operate in, women cannot drive, and in some of the cities that we operate in, women cannot share ride with men. That reduces the number of the products that we can offer to our customers. We call our drivers who drive the cars on the road captains. This is something that the word driver has a negative connotation in the region that we operate in. So we wanted to change that, and we wanted them to feel as part of the Careem family, and we also want them to become entrepreneurs and expand the ecosystem by improving their lives and by eventually over time making money to buy their own cars and running their own fleets. Now, let's just understand the ride-hailing problem a little bit. So ride-hailing problem has two personas, captain and customers. Customer is someone who wants to move from A to B, whereas a captain is someone who has a vehicle, be it a bus, a car, or a tuk-tuk, or a motorcycle, and wants to service customers and make a living. Now, connecting the two together is what we call marketplace. It's actually a conduit where we match customers with captains. Now, due to the nature of our marketplace, we have to take real-time decisions, and that actually requires us to build systems that can support some millisecond lookups and fast computation. Now, customers and captains need to be matched very quickly, because in this day, customers don't spend a lot of time on your app. And the cost to switch is very easy. Customers can change their mind, hail a cab, or worse, move to competition. Now, the marketplace itself has three important aspects: reliability, match quality, and tracking. Reliability has different meanings for different personas. For customers, it is the trust that they will be able to get a car anytime and anywhere they need it. For captains, it is a trust that they will be able to use the platform to make a living and improve their lives over time. Now, match quality is someone, we define it as a captain who can reach the customer in the shortest amount of time with spending the least amount of fuel. So you need to pick the nearest captain to the customer. Tracking, as I said, our region is a bit security challenged, so our customers require the ability to track their rides or track the rides of their loved ones if they share with them. So this requires us to ensure that we are able to track our captains in a very real-time nature to drive home that advantage. Now, basics, connectivity on the side. So when we started off, captains in the region are very humble, come from impoverished backgrounds, so they cannot afford these expensive Samsung or Nexus devices. Now, what results is they end up using low-end Android devices, and low-end Android devices keep their costs down by sacrificing on the GPS chip quality or CPU processing itself. Now, the bad GPS, these low-quality GPS sensors, add a lot of noise to our GPS readings, which makes metering and tracking really difficult. we operate in a region where temperatures are normally between 46 degrees centigrade to 56 degrees centigrade in the summers. That means these metal-based phones, some of these metal-based phones can heat up pretty quick, and that affects the CPU, and that in turn affects the performance of the app running on the phones. And the bigger disadvantage is that data is not cheap in that region. It's actually quite expensive, very expensive to begin with. And most captains can only afford something 1 GB per bun, which highly limits the solution space that we for our solutions. Number one, we will like to then make solutions where the services are non-chatty, that the devices and servers are not communicating with each other frequently. Now, these bad GPS sensors also dictate that we use a functionality called something called snap to grid. Google offers it, OSRM offers it. So that requires us to store some previous pings of a captain as well to reduce the noise from the ping itself and get a more accurate location out of the mix. So this plays into the factor that how much data we have to store and how much data we have to crunch through to deliver a compelling experience. Now, we will walk you through a few takes that we did on the eventual solution and where we started off. But before we go into that, let's define a few metrics that we measure the success of our solutions off from. ETA. Now, ETA has two dimensions. One, the ETA that the customer sees when he or she books a car or requests a ride, and the actual ETA that the customer gets. Now, to have a very high, to deliver a very compelling customer experience, you need the delta between the two to be as small as possible. Because if the delta is as small as possible, then the customer is getting what he sees, which is a big advantage in the region where competition is a bit tough as well. Now, time to match. The reason is because, as I said, customers would not spend a lot of time on your app. So if your process to find a match takes about minutes, whereas a customer can only spend 3 minutes, will spend about a maximum of 3 minutes on your app, then you have wasted 2 minutes of that precious time just finding a captain and then making sure that the captain wants the ride or not, or can be matched with this captain after the filters or not. So time needed to make the best match is also very important. Tracking. As we said, tracking in our region is very important. So age of captain location plays a big part. So when you're tracking, your ping, the location that you show or the customer sees of a captain needs to be real time. It needs to be as close to its physical location on the network itself. So let's say a captain ping 3 minutes. If I'm collecting pings of captains every minute, then if I'm showing the customer captain's ping, the total duration ends up between 3 minutes from the ping and what the customer sees. So a customer is actually may actually see a ping which is 3 minutes old, which does not really work well in a security challenge region as well. Then ratio of request match. This is how many people were requesting a ride and how many requests we were able to serve. Now, this also depends on the supply that we have on the network. But assuming that we have constant or enough supply to meet demand, then this metric drives, it gives you a really good insight on how the system or your algorithms are doing. So we believe in simplicity. So when we started off, we said, how do we get captain's data on our network? So we used the simplest solution out there. We had a captain app that sends pings in a JSON format to the server stores in MySQL table. Really simple, easy to get off. We were able to get it up and running within the days. Now, before we go into how this solution worked for us, let's just look at the scale when this happened. So we had about 19 cities, 500,000 customers, 9,000 captains, and these customer captains were making 1 million ETA requests, approximately 30 million pings, and 16 million lookups. Now, some of the issues that we faced while using this solution. So first and foremost, we faced continuous deadlocks and performance issues while using the solution. So we had a table which stored a captain data and the captain last seen data together, so the coordinate. Now this row will always be updated by multiple operational processes, meaning the customer's match, the last string. So different transactions are updating the same row, and MySQL has a weird thing that it locks it up. So we ran into this downward spiral where with performance issues, you will go into logs, the application will start freeze, and we will suffer a downtime. One of the important aspect that we found was we started with MySQL 5.6, but had no geospatial support, which means that looking up nearby captains was not trivial. The reason it was because coordinates is a multi-dimensional value. You can if you use the latitude, longitude, with my 5.6, you have to you actually stored it using 2 columns, latitude and longitude, and indexing them was a problem. And the only way you can look up nearby captains were using something what we call the Haversine formula by calculating straight line distances, spherical distances. That made the lookups pretty slow. So in the end, for stability, because of the issues that we were facing, we had to reduce the number of pings that we are getting each minute, and we reduced to 1 ping 1 minute. Now, all this affected our ETAs and customer experience, plus the cost balloon in respect to what we were getting out of it, because we were using over-provisioned servers to avoid deadlocks by throwing a lot of CPU power on top of it. Now, this graph gives you some idea of what we were able to get, that the actual ETA that we were seeing, customers were seeing, was about 11 minutes. Promised ETA had a higher delta between the two. The time to match was about 3 minutes when we started off. Now, it worked for a bit, but it was not a great solution. Now, the most important aspect, we were only able to serve 40% of the requests because customers will switch, because we were taking a long time in making that match, plus because of the reliability issues that we had with the system itself, a lot of people just didn't use our service at that time. And the uptime was not very high. Now, some things that we learned on the go. The market that we operate in, or the business that we use, is highly volatile. Each government has its own set of regulations. Each city presents a different challenge out there. So what you foremost need is an ability to modify or alter your schema at will. With the high transaction table, MySQL table, altering a schema is not trivial. You will have to take a downtime or shut down your system to ensure to update those schemas. And we wanted an ability, so we decided that we needed an ability to alter the subject schema at will. Now, data is volatile. A ping is relevant only for the next ping, till the next ping comes in. So if we lose that ping after that, then yeah, it doesn't hurt us, because we only need the most recent location for dispatching purposes. Plus, so as ride-hailing works, and you will see a spike in traffic in the morning rush hours or during the evening rush hours. So you'll see a lot more captains coming online, a lot more customers requesting rides. And that is where we knew that we need a buffer to actually deal with these spikes and to be able to process all pings accordingly. Second, we needed a mechanism to represent coordinates as a scalar value. Having them as a multi-dimensional value was limiting our solution space. These were some of the learnings from our take one. Now, while building the next stage of a solution, we decided on a few things. We are going to be schemaless because we are constantly changing. So we wanted the ability to change the schema at will. We wanted to use buffers, so that's where we said, let's use SQS as buffers. And then DynamoDB. So this offered us to store captains for a long time per system. And we used ElastiCache to store captain pings in memory so that we can look them up in a faster way. So why Redis? Redis has a unique architecture which results in more cleaner and more elegant code with fewer lines, plus it's a lock-free architecture. And though runs, it's single-threaded. That has some issues on its own, but yeah, it's a pretty much lock-free architecture that alleviates a lot of the problems that we were getting with constant updates to the same row by multiple transactions. It has a very rich data set, strings and sorted sets. You can use sorted sets to sort on the database level rather than on the application level. And data structures, there are built-in data structures that process data optimally. You can use a few more tricks like pipelining and primary replica configuration to speed up the performance of your application, if need be, without actually expending more on the infrastructure or hardware. So why we chose ElastiCache? In-memory key value pair, because our captain location lookups were key value. So given a captain, there will always be one last seen, so key value store. It has high performance. You can look up millions and millions of records over a short amount of time, delivering some millisecond latencies. That helped us pretty much. Fully managed. So as you said, we were starting up and we wanted to spend more time on solving the business problems rather than handling the infrastructure side of it. So we are big fans of managed services, and that's where when we evaluated it, we were blown away by a lot of performances, but it was highly available and reliable. It offered a lot of things out of the box that we didn't want to worry about at that time. Plus, we were able to save a lot of developers, 25% of developers' time when building or rolling out solutions, because yeah, it's there, launch a cluster, and then let's solve the problem that we want to really solve for the real world problem. So this is how we then build our solution. We had captains, apps sending pings to a queue, which were processed by a worker. A worker stored these pings in a cluster, that is cluster itself, and to a DynamoDB as well. So what we did, one more thing is, so in our network, we are operating out of 17 cities. Some cities are far bigger than other cities. So we have dedicated specific clusters for those cities and countries, and bunched all the remaining to one. So that's what ROW, rest of the world. So this is how our data structures look like. Key, deterministic key, so that you can, given a captain ID, you can easily compute the key, and then given the key, you can easily get the data within a millisecond. Now this is what we call very interesting. So we said the primary problem that we wanted to solve for is finding the nearby captains. And to do that, we identified that we have to represent coordinates as a scalar value. There are a few standards out there that you can use. We went with geohash. So geohash is a concept that can compress a string or represent a coordinate as an alphanumeric string. It also has its depth. So a geohash string can be at most 12 characters. So a 12-character pings is the most granular level of a coordinate. And if you start removing characters from the end, that you will start getting a bounding box from that coordinate upwards. We went with 5 characters geohash, which means AABC, which gives us a bounding box of about 2.7 kilometers. So, and the reason we did that, because a lot of our dispatching algorithms, the radius that we had defined were about 3 kilometers itself. So 2.7 was a very good, was very close to a business objective as well, how we were dispatching really. So what we said, so a captain ping comes in, we get the coordinate, convert into a geohash, take the geohash group, 5-character geohash group, find which products that this captain can serve, because we have some offerings like economy, business, business plus, and then add this captain to all those sorted sets. So the key becomes very deterministic. The customer side can also make this key, compute this key. The captain side can also compute this key. And we add the captain to this sorted set. Now, sorted sets offer you an attribute which you call score. You can use, it's a double value, and we decided to use the timestamp when the captain last ping as a score. So what this offered is, so when we wanted to see all captains within a geohash or within a location, nearby location, and we wanted only captains that have pinged within the last 30 seconds, we just did a computation. Hey, look up this sorted set, current timestamp minus 30 seconds, all cap keys with a score greater than this, returned a sorted set out of the box, which was pretty good, because we don't then have to go through all the captains and sequentially, all in parallel, filter them out. So now, this captain was in the geohash AABC, and let's say when he pinged next, he moved to the next geohash, which was AABD. So this is how he will move through different sorted sets as an indexing, in an index fashion. So we will remove it from the previous index and add him to the new index or the sorted set. This is how our dispatching would look like. So when we were dispatching, we would dispatch in a grid of 3 by 3, which means from any point, a maximum area we covered was about 9 kilometers. And with geohash, the libraries out there, it's very easy to compute the neighbors of a central geohash as well. So let's say if the customer it's a dark green spot, and the red-green spots are ineligible captains because they may be busy with another ride, or they may not be serving the same customer, the product, and all the other greens may be eligible captains. So that we were able to get this list of captains in a very, very quick time, milliseconds, and then, then we can use that the amount of time that we save, we use the same time to apply additional filters by using OSRM matrices, Google services to get the best captain that can reach a customer the fastest. Not distance-wise, but time-wise, that will reach the customer the fastest. Now, when we built this solution, our scale was a bit different. We were in a lot more cities, 6 million customers, a lot more ETA requests because people like to see where the nearest car is. So in the region, people compare where the nearest captain is and go with the provider which is offering the nearest captain or the fastest captain. Now, with this, we were able to reduce the time to match, the ETA, and we were able to make sure that the delta between the promised ETA and the actual ETA was constant across time. So this was pretty much what we were hoping for. Reliability went up. We were able to serve 86% of the requests. And beyond this point, it actually then becomes a function of supply. So the system or algorithm was doing what was asked of it to do. Uptime, we went to 100%, nearly 100% uptime because we were not facing logs. And yeah, this is just an insight into how fast our lookups are using our monitoring tools. Now, what this really meant is we were able to ping more frequently, 15 seconds, every 15 seconds, and 4 per minute, improve ETS because we were pinging so nearby each other that snap to grid, the performance for snap to grid increased because you had far more pings closer to each other. That meant that it can reduce the noise out of those pings pretty much well, and we were able to get an accuracy of even down to the lane level. Now, once you have a very accurate picture of where the captain is, you can, your algorithms can then decide who the best captain is because they have reduced the noise. And in some of the cases, we noticed the noise could be as much as 1 kilometer in the pings itself or the GPS coordinates itself. Side benefit granular level tracking for customers improved because they can, with a very high certainty, they can know where the captain actually is. The average age of the location that a customer was seeing was down from 180 seconds to about 45 seconds. That was a big win because that's as close to real time as you can get. But the most important thing that we were able to do is we were able to save time while matching. So previously we had to look up across the database which captains were nearby using a straight line distance, etc., and then filtering them. Plus, with this approach, since we were able to get a lot of captains far quicker and apply additional algorithms on them, so we were able to reduce the time to match about 15 seconds. This was that if a customer pressed get right, it will take him about 15 seconds, worst case, to get assigned to a captain. So that was a big one. So let's look at what our stack was. We are predominantly Java company. We use Spring Boot as a lot of framework because the ecosystem is pretty rich, and we deploy majority of our applications as Elastic Beanstalk applications. So let's dig into some of how what Redis offers in general. So Redis comes in 3 major flavors. Standalone, you just set up your own single standalone cluster and read it as both for reads and writes. Primary replica, so it works the same way database replication works today. You have a primary node, and then you have replica nodes that it's replicating out of. The best thing is that since this replication is also built in memory, it's quite fast, and in our time, we have never experienced a lag, or whatever lag we have noticed was in milliseconds, so you can discard that lag. So it was pretty fast, and you can scale out reads pretty quickly as well. Cluster Redis. Now, this is the only data source that I know of that offers sharding out of the box, and where you can shard with, it does not require your applications to know how your data is sharded. So it's application agnostic. So that it offers a lot more flexibility and a lot more advantage over the data sources. So when you're setting this up, a few things that we should always take care of. Have multiple replicas in your cluster. And standalone mode works well for a lot of for some basic use cases, but for enterprise or a consumer level application, always go for the minimum as a primary and replica configuration, where you have multiple slaves in your cluster. Always configure a backup from your replica, because if you configure backups from your master, it will take, when the backup starts, it will take down your master node for a few minutes. It will load all the data that's in memory and start backing it up, and your node will become unavailable for 2-3 minutes. And if you are a constantly serving business, that may mean a downtime for some of your critical processes. If you're using AWS ElastiCache, never connect directly to the master node. Always use the endpoints that they have available, because if a failover happens, your application would not need to be not need to do anything. It will happen behind the scenes, and things will still keep working. But if you're connecting directly to the master node and writing directly to the master node, connecting to it, and then if the failover happens, then you might start seeing that we are unable to write to a read-only replica. Set aside 30% of your memory for a lot of Redis operations. Else, if you start when you start to take a backup, it will take more time. When it's going into recovery mode, it will take more time and eventually cause you downtimes as well. So scaling. So with Redis, single point of if you use single node, it's a single point of failure, and you will never be able to scale out. Always remember, Redis is a single-threaded application, so no matter how many cores your server has, doesn't matter. It's single-threaded. It will max use one core. So to read scale out, the recommendation is you read from the slaves and write to the master, because the replica lag is non-existent. It's virtually non-existent. So you can use that to your advantage and scale out your reads pretty much. So what we did was we wrote our own library. What it does is figures out all the read endpoints or read nodes in the slave, and connects our instances to, divides the full application across all the nodes. So we use all the nodes the same amount of times. So let's say our instance or our application has 12 instances running in an Elastic Beanstalk application, and we have a Redis cluster with 4 replicas. So at max, each cluster, each read replica will be serving 3 instances at max. So that scales out your read pretty evenly and pretty well. One thing that we learned over time in the hard way was getting the most out of any Redis configuration or any hosting is choosing the right library. We started with Redis. It was the most basic library out there, but it did not serve a more of advanced use cases. Choose the right client library. That's pretty important. So now we are still growing. We are growing like crazy, so we still need further scaling. So now we are working on a few products that require us to ping more frequently. Now, previously, when a captain started a ride, that captain's location, we didn't need that data as fast as we needed when the captain was not in ride, because when a captain is assigned to a ride, it's basically undispatchable for us, unless and until that ride finishes or the captain is available back to it. But we're working on a few products like pooling, where the same captain can be matched to another booking as well. That means that even in ride, the frequency of pings will not go down. That means we'll be processing far more pings, even though maybe we're serving 86% of requests, we'll be serving, processing far more pings than usual. Plus, the business wanted to go to a very minute level of ping every 5 seconds. That's a big ask, because that suddenly increases the problems faced by 3x just by going to 5 seconds. Because the reasoning behind was still, that the gains that we saw by going to 15 seconds, if you go to 5 seconds and use the last 6 or 7 pings with snap to grid and the factors, we'll get a highly accurate location. Plus, then maybe we can avoid using GPS and use something which Android has called fused locations, which has a higher chance of noise, but still works in worst conditions as well. So that's what we want to do. Now, but other side, we had far more captains on the road itself, more captains reading captains' data for tracking other purposes. The business wanted the same demand, the performance in terms of promised ETAs, the delta between ETAs, time to matches, etc. But as a tech side, we wanted to ensure that all the writes and reads are more balanced, and we are getting the max out of the provisioning costs that we are spending. Just a few numbers to see out where we are now: 80 cities, 15 million customers, 500,000 captains. These are active captains, actually. The number of captains may be longer, but these are active captains on the network on our peak time. So we had 15 million ET requests, but because a lot of people now compare businesses. Okay, the competition is a captain 1 minute away. Now you have a captain 3 minutes away. So you will see a lot more ETA requests, a lot more pings, because we are going to a greater, very frequent pings, and a lot more lookups because of the growth in business. Now, we did a few problem solutions out there. We looked at a few things. The primary sharding that we had, where we were separating, we had dedicated few clusters for some big growth countries. They became a problem in themselves because they became so big that even at the country level, they were not good enough or not small enough for a problem to solve for. Plus, we were going in more and more cities. So maybe a country like Pakistan, who we have 16 cities, will have a lot more sorted or geohash indexes versus a country like Bahrain, which has just one city being served. So the problem was getting compounded with more cities that we go in. So we started looking at, we just identified sharding is the way to go. So how best should we shard? Should we go to a city level and have single Redis clusters on each city or zone level? That could work out of the box because we already had a platform that was working. We just needed to change configurations. But the downside would have been that the provisioning and management of those clusters will become a pain because 80 clusters, 80 cities, big cities like Karachi, Cairo, Riyadh, maybe multiple clusters in the city, it will become a provisioning and management nightmare over time. So Redis with 3.0 has a cluster mode. Sorry. So a cluster mode is basically multiple primaries in one big cluster, and you can shard data across it. So it has slots, hash slots, I think 1599 or 16132, and it distributes. You can distribute them equally across different shards, or you can set, hey, this shard, this number of slots is for this shard, this slots is this shard, and depending on needs. So it uses a CRC algorithm to convert your key into a hash slot and then sends it to the right shard or primary. Now each primary can have a lot of its own set of replicas, and we can have a lot of number of shards. And plus, the biggest advantage is still application agnostic, so you don't need to really change your application code per se and to take advantage of this. That was a big win when we were considering this. So we went with this, but when we started using it, we ran into a few performance issues as well. Because if you are using a shard and if you don't know, so when you're looking up at data for captain, it will ask for all the shards in the cluster that do you have this data or not. Now, you can avoid that by using hashtags. So what a hashtag does is the text between the key, it only translates this part into a CRC rather than the full key. So then basically you can use this technique to co-host a lot of data that you require to be read together or has a very close association with each other. It will offer you a lot of advantages over performance in some cases because, yeah. So this is how our solution looked like. Still the same, pings coming into a queue, worker processing it, but now instead of a single clusters, it's going into different sharded clusters. That's how we were able to scale out different countries, even if they were, even if we added more and more cities to the mix. If we added more cities, it's just adding more primary or more shards to that cluster to, have a scale out ASAP. So performance remained consistent. That was the biggest advantage with spending minimum amount of effort. We were able to keep the same performance that we were able to derive from the previous solution. So, sorry, that is it. Any questions?